so that they can tell, oh, right away, is it safe or not? And it would save a lot of time for people like us. Also, because we work with key set, one thing that I forgot to mention is, if you use this API, what happens if someone tomorrow found that ASGCM is broken? You cannot, how could you fix it? You have existing data. Like, you have to recombine everything. You have to change the code, and sometimes you don't have the source code anymore. So, we fix that problem by always working in a key set, like not in individual key. And each key is bound not only to the key, raw key material, but also the algorithms, all the parameters that we need to successfully get a new instance of the primitive that we want to provide. So for example, as starter, the user can use a key set containing a single key, a single ASGCM key. But if ASGCM is found broken, they can easily roll over and move to a new algorithm without having to change anything in their code. They just need to change the key set. And that emphasizes a very important lesson in crypto, for example. Like, you know, in crypto, the things that we use today may not be the things that we use in 10 years. And history has shown us, like, you know, attacks get better over time. Like 10 years ago, when Linus Torvalds designed Git, SHA-1 is still strong, but now it's broken. And then it's very hard for Git to move on to SHA-56 because SHA-1 is like hard-coded into the implementation. So we don't want to make that mistake. We want to make it very easy for people to move on, to plug, you know, replicate the standard, to move on to new things easily.
Okay.
So this is like how we move, like how we make sure that people cannot use the dangerous API anymore. So we use static analysis. We run it against our entire code base, and we add existing user to the wireless. And then we make sure that engineers can no longer use the dangerous APIs. If they use it, their code won't compile. And they have to talk to us, and we will tell them, no, you can't use it. Or we will give them an exception. If they have really good reason, and it's okay, it's safe, in their use case. But this is the only way to deal with this problem, this at our scale. We have to make sure that insecure code cannot combine. So,
I have a few more slides.
So the last thing that I want to mention is we use a lot of third-party crypto libraries. We build things on top of the OpenJDK API. We build things on top of OpenSSL, RC Cache. But the problem is we found that like these APIs, they usually have a lot of problems. They're usually developed by non-cryptographers. They're developed by normal developers. And they have a lot of bugs. And the bugs happen very frequently and stay there for a long time. So we found bugs that, you know, last for maybe 10 years. And when we tell people to fix them, they fix them up. And then after we upgrade our library to the next version, we found the same bug again. So, and it's happened again and again, not only like in the libraries that we use, but in all the libraries that we take time to look at. So, and the reason is, you know, in programming, usually the way people learn programming is, you know, the best way to learn programming is look at the code of all the better programmers, and you try to mimic them, and you try to copy their style. But if you look at crypto code, it's not obvious, like, because of the constraint that we have, like, you know, fixed timing, or you know, gas-free lookup. The code looks totally not obvious, and it makes it very, very hard for someone to copy the practice. And good implementation guidelines are very hard to find. And people have to read, like, survey the literature for years to spend decades, you know, going to conferences like this. And developers don't go to conferences like this, right? So it's very hard for them to keep up with what the latest attacks out there. So we look at this problem, we ask ourselves, okay, how can we help? And the thing, we find out that, well, developers, the way developers deal with bugs is they write tests, right? They write unit tests. They don't they don't fix bugs by reading, read the papers. They write unit tests. So why don't we just, read the papers and implement the attacks in those papers and provide them, unit tests. That's exactly what we do. So we basically survey on the papers that we found and implement on the attack vector, like on the implement unit tests that implement the attacks in the paper or the expected behavior of the library. And then we just run the tests against all the libraries that we use, and we found, a lot of bugs. We found I stopped counting, but I think we found more than 50 bugs, and some of them are pretty dangerous. Like there are bugs that allows people to extract the private key of ECDSAs. If I have time, I can go more into detail of those. But we have tests for the most popular crypto algorithms. Anything that we found we use or we found people using, we have a test for them. And Daniel Beijing is one of the developers behind the project, and he's very carefully surveyed the literature, implement the most known attacks, invalid curve attacks, bias analysis, and of course, all the Beijing attacks. We have, I think, more than 100 tests right now, and we provide the tests in form of text vectors so that they can be ported to all the platform, all the languages very easily. So, yeah, I think that's it. I don't have. I think we don't have time for Q&A. So yeah, basically that's what we do. We build API on top of third-party libraries, and then we make sure that the third-party libraries are safe against no problems. And I think the takeaway is, well, you want to make sure that insecure code cannot combine. And if people want to do something dangerous with the code,